He says it doesn't make sense, but I'll bring it up to tax.
I don't think it makes sense.
But so this is from 400, right? But I was thinking, is the reason why classes, why they receive a semicolon simply related to the fact that they're like an extension of a struct, and structs take semicolons afterwards?
A struct does take a semicolon after.
And
But I thought the class does not need a semicolon.
And it did today.
Yeah,
It
Fox
does?
said today.
Sorry?
Fox said today, and he had it up on the
Yeah.
at the end of
That
it.
it needs a semicolon after the end curly
Yeah.
brace?
For what language?
For
Stay
C++.
present.
Right, let's find out.
Yeah, I'm pretty sure you need it.
Well, yeah.
Yeah.
Yep, it does.
I'm starting to question my education.
Because he said, let's not go to the murky places where you dwell. You don't know what he's doing up there.
Down in Texas.
Yeah.
To be-
He's like, well, maybe that's what goes down in the world of
Well,
tax,
a struct in C++ is a class, but by default all members are public.
Wait.
Yeah, that's what he.
No, he said they're private. He said
Well,
by
no.
default.
No, in a
classes are
class.
private.
In the class, that's different.
In a struct,
Oh, but it's
struct.
and C++ does not become. Oh, it is.
A class has both. A struct has both.
You just don't have the light? No? Because if you are going to write down anything, you probably need some light. And I don't want people to wear those weird, minor, bicycle, cyclist type of lights. Or break out one of those things, how do you call those things? Or worse yet, go to the trunk of a car and bring out a flare and bring it into class. That would not be a very good thing to do.
I think that's a liability.
Yes, that would be a lot of liability. Now, if you take one out of a boat, then it's even more of a liability. Because it is a gun, you can actually launch that thing,
Yeah, I think it actually stopped liability. That's just an arrest.
All right. So I'm hoping some of you had time last week, over the weekend, to kind of play with the simulator, or at least take a look at the parts that deal with the registers and also the ALU. Okay, I'm not sure whether you guys have time to do it or not, but that would be a good thing to do over the break and over the weekend. So what we'll do today is the continuation of the discussion of the control unit. We'll keep using the processor that I designed, and today's focus is mostly on the memory bus. Okay, in other words, now we know how the registers work, and we know how the ALU work. But how does it get information to process? How does it get instruction to instruct the processor what to do? So that will be the focus today, and we'll see how far we can go today, and that will determine what the homework I can give you on Thursday. All right, so let's go ahead and get that started. And I'm just double checking the recording here. I did end up putting the audio part and the screen recording part from last week together and upload it. It took me a few tries. Okay, the few tries did not have anything to do with lining up the video with the audio. I could get it done pretty quickly. It's the format that YouTube would take. Okay, I exported to MP4, and I thought MP4 is MP4, right? Nope, not really. I uploaded to YouTube, and within half a second it says, "Nah, cannot do this, wrong format." It's like, but it's MP4, not wrong format. Then I tried out many other combinations and eventually found one that worked. So that's why it took a little bit of time, because every single time I re-render into a different format, it will take me a long time to re-render or transcode the content. Even though it's really the same content, the transcoding part takes a lot of time. Yep.
You use if it's an Intel processor, you should see if it has QuickSync. So it can do like 200 plus frames a second.
What's the name of that software again?
If your processor supports QuickSync,
quick sync.
And you use a program like Handbrake, you can transcode really fast.
Okay, I'll take a look at that. I was using KDE and Live, which may not, be using all the quickest tools. All right, so we'll go ahead and take a look at the design again. I don't have a folder. I think it's in downloads, tags. Nope. Okay, never mind. Download it again. And do it on the other one. Hey, it is here. So it's in my home folder. Okay, there we go. There we go. Yay. All right, so we are now back to the design of the processor. And today's focus, as I said a little bit earlier, is going to be on the memory bus. In other words, we want to look at this thing here, okay, which is not this little thing, it's the overall, that's the memory module. Let me change to a pointer here. That thing, okay? So that's basically one single memory module, and I'm not using multiple memory modules in this particular design, just to keep it simple, okay? But we already talked about how to make a memory system that makes use of multiple chips by using a decoder to deal with the chip select input of multiple memory chips. So that part, we kind of know how to deal with it. So for simplicity, this particular processor only has connection to one single memory chip. So the focus really is how do we coordinate the timing of, okay, the processor wants to go to that location. So how do we route the address bus, and how do we route, most importantly, the data bus to go between the memory module and the rest of the processor. So that's going to be the focus of today's lecture. All right. Are there any questions from last time? Okay. If you have not watched the lab portion from last time, you might want to watch it, especially if you have questions about what is a multiplexer, what is a demultiplexer, and what is a decoder, all those subcomponents that we made use of last in the previous class, because I spent some extra time in the lab to explain what those subcomponents are and how to make use of those subcomponents. So if you have questions about the subcomponents, you might want to refer to the lab portion from last Thursday's class. All right. All right, so we'll focus on one thing at a time, and the first thing we'll do is to take a look at the address bus, okay, which is this thing here. So the address bus, once again, is what specifies which location of RAM do I want to access, I being the processor. Okay, so the processor has to specify at some point, okay, the content on the address bus, which is a whole bunch of zeros and ones, but collectively they specify a location on the memory chip in order to specify, okay, I want to either read from this location or I want to write to that location. And you can see, the thick line is being selected, but it doesn't really go into any particular real component. It goes into a mux, okay? It is not a demux, this one is a mux. This mux is fairly simple. Okay, if I click on the mux here and show you the properties. So this mux has one select bit, which means it is only selecting one of two things from the input in order to become the output. But the width is 8-bit. In other words, we are dealing with the address bus of this memory chip, which is 8-bit wide. So if you click on the memory chip itself, it also tells you that the memory chip has 8-bit as the data bus, which means each location of this memory module stores 8 bits or 1 byte. It also tells you that the address bit width is also 8-bit, which means it can store 256 locations, each location being a byte. Are we still doing okay so far with understanding this portion of the picture? Is that okay so far? All right. Okay, so let's go ahead and focus on the mux here, because we want to figure out, okay, so how do we specify the content on the address bus? There are two ways. And the two ways are necessary because we want to be able to do both of those things. So this is one line, okay? This line going into the mugs is coming from an automatic adder. If you look all the way down here, this is just a regular adder, okay? And this is the mechanism to automatically increment a particular register so that we can go to the next location. This is a register. PC is a register. Let me see if I can just magnify this portion a little bit. So this way we can see the connection a little bit better. There we go. Okay, I think this is better. Okay, so let me just kind of specify what these lines are. This is the output of the mux. It goes to the address bus of the memory chip. Okay, so what we want to know is what are the input into this mux here. One input is coming from here, and there are two ways to control the output. There's this output, I take it back, this is the input into the adder, and this is the only thing that can drive this line here. In other words, the Q port of PC as a register is driving this side of the mux. PC, just like our registers in the register bank, register A, B, C, and D, is a particular device that can store content on its own. So right now it is storing the content of 0, 0, okay? But you can also update the content of a register by presenting the new content into the D port, and then you have to specify enable, which is the EN, and then you have to go from a low to high clock in order to update the content of the register. Okay. Are we still doing okay so far? Because we talked about registers last time. Do we still remember, what a register is and how to make use of one?
Yes.
Okay, that's good. All right, but this one has a kind of an interesting connection. So if we are focusing on only this part here, okay, let me just zoom in two more levels just to zoom into this part here. So the rest of it, would not distract us as much. This is PC, and PC is the abbreviation of program counter. This is the address of the next instruction the processor needs to read, decode, and execute. In other words, it is a bookmark. Okay, it is a bookmark in an operation manual to basically say this is going to be the next instruction that we need to execute. Well, this is the page number of the next instruction that we need to execute. Are we still doing okay so far with this? Now, if you have used GDB or any type of debugging aid in even code blocks, this is basically the highlighted line, okay? Because it's the next line or the next instruction, the next expression that it will execute. Okay? So if that is the case, why do we have something like this here? What is this adder doing? Let's take a look at how the adder is connected. This port of an adder is carry in. So the carry in is actually hard-coded to a 1. Oh, okay. That's kind of strange because we normally do not do anything like that, right? And even more strangely, the input of the adder is hard-coded to 0. So it doesn't seem like, this is a regular adder. Well, in fact, it is not being used as a regular adder. It can only add 1. Okay, each time we clock it, it can only add 1 to get to the increment. Exactly, it is only doing increment so that we can get to the next location. That's all this adder is going to do. The output of the adder, or the input, okay, let's talk about the input first. The input of the adder is the output of the PC, or the program counter register. So this is the input, oops, okay, so this is the output of the register, and it goes into the input of the adder. So we are basically just adding whatever the program counter has. We're adding 1 to it, and that becomes the output of the adder. But if you look at the output of the adder, it doesn't go all the way back to PC all the time by itself, because this line kind of goes all the way around and it goes into another mux. In other words, sometimes I can say, hey, I don't want to get the PC plus 1 and store that into PC. Sometimes I have another way to specify the program counter, but not all the time. If I do choose, this is the select bit here, okay? So if I do choose the PC plus 1 input here to present to the output, then the D port, which is the input to the register, will have the value of the program counter plus 1 presented as the input. But that by itself is not going to do anything, right? Because in order to update a register, what are the two other things that I have to do? A single register. So if you look at PC here, okay, PC has 5 different ports. The reset counter, the reset pin is not going to be useful because we don't want to reset it unless we're resetting the whole processor.
So you're talking like the selection process, where we have to select which register we wanted,
right?
And then
yep.
the clock.
So we have 2 other things that we have to deal with. The first one is to enable. Okay. So if enable is a 1, that means okay, now the register is starting to pay attention. So if enable is a 1, and then we have a, sorry, this is not the enable pin. This is the enable pin here, okay? So enable when 0 clock triggers are ineffective. So I first have to assert enable, and then what I will do next is to have a 0 to 1 transition on the clock pin. That will update the content of the PC, and if the input to the PC register, the D port, is coming from the adder itself, then I will be updating the register to 1 more than what it used to be.
But I see. But if we're jumping, how we end up.
Okay, so let's build a subcircuit just to illustrate this point, okay? Because I want you guys to actually be able to see how we can make a subcircuit, and its only purpose is to say, okay, every time I clock, I want to be able to add 1 to the value that is being stored in a particular register, okay? Because this is a fairly useful subcircuit, and I can do that by just saying, make a new file, okay? The other file is still around. I'm just using this one as a new one, and we'll go ahead and pick up arithmetic, just a regular adder, okay? And we'll go pick up a register, which is a part of the memory components. So we'll pick up a register here. And this time, I'm not even going to bother with the mux, okay, because I only have 1 single input. So what I will do is I will build the circuit the same way as what I did earlier in the other one. And go to wiring, have a constant of 1 as the carry input, and also pick up another constant to be the input to the whole thing. Now, if you want to, you can also specify 0, 1, or an 8-bit 1 as the as the input to the adder, and the carry of 0. It will do exactly the same thing, because all we want to do is to keep adding 1 all the time. So there are 2 ways to specify how to add 1. But I'm going to do it the same way as before. So I will change this to an 8-bit. And the value is going to be 0, 0, and connect that to the carry, one of the inputs, and then this is going to connect to the carry in. The output of the register is going to connect to the other input of the adder, like so. And this is the output, and I'll do 2 things with the output here. The first thing I will do with the output is I'm going to bring it back to the input of the register, but I will also do one thing to make it easy to visualize what is the content of this particular bus. You can always hook up, this wire to a pin. So in this case, we have a pin. It is an output pin because it is the output of the adder, and we have 8 data bits here. And let's see, tri-state no. Okay, that's good. We'll make it face east. Nope, the other way. We'll make it face west, and we'll hook it up. So this makes it easy to visualize, what is the output of the adder. So right now, it all makes sense, right? Because the register has a content of 00, which is in hexadecimal, which means it is just all 8 zeros in binary. Now we do okay so far with the output from the register. The other input of the adder is hard-coded to 0, but the carry in is hard-coded to 1, so effectively the adder is really always adding 1 to the only one input that is effectively hooking up to something that is useful. And that's why the output is 0, 0, 0, 0, 0, 0, 0, 1. Is that okay so far? Okay. So the next thing I'll do is to hook up all the other wires. The reset pin, I'm not going to bother with it. So what I will do is to hook up something to the bus line here. Okay, this is the this is the clock line, and I'll just hook up a pin to it, and I'll just hook up a pin like this. Make it line up. Okay, so that's the enable pin, and we'll move it down a little bit. Ugly. And then we'll have the enable pin to hook up to another input pin. So pick this one, hook up to the input pin here. All right, there we go. So now we have pretty much the same subcircuit as what we were looking at in the overall processor picture, except this one we can just kind of click on things and experiment with it, right? So right now I can clock, or I can toggle the clock pin all day long and nothing happens. Okay, let me show you what I mean by toggling the clock line all day long. Yep, simulation mode. See, nothing happens, right? And that's because the enable pin is a 0. The register is not paying attention whatsoever to the D port, which is the input port, or the clock pin, which is the only indication. From 0 to 1, that transition is telling the register, hey, pay attention to what is in the D port and update your content to whatever is presented in the D port. On the other hand, if I change the enable pin to a 1 first, then every time I have a 0 to 1 transition, it will add 1 to the content of the register. So focus right now, okay? Click, see how this is now changed to 0, 1, because it used whatever is in the D port to update the content. But as soon as the register is updated to 0, 1, which is 0, 0, 0, 0, 0, 0, 0, 1 in binary, the output is updated instantaneously. But the output of the register is one of the input of the adder. And now we are adding 1 to 1, and that's why the output of the adder is now specifying the quantity of 2. Well, in binary, but it's basically the quantity of 2. Are we doing okay so far with all this stuff? Okay. So if I keep the enable pin enabled, which is this one here, if every time I go from 0 to 1, the register is going to add 1. Okay? Yeah, every time I clock it, right? Every time there's a 0 to 1 transition on the clock line, it will take the new value, which is 1 plus the current content of the register, and it will clock it in to the register and therefore updating the content of the register. So this is a fairly simple mechanism to have something that has the ability to update itself. It's basically a plus-plus mechanism, if you will, if you borrow that term from C++. Do we have any questions about this little subcircuit here? Because we will see this subcircuit not only once, but at least twice in the processor design. Go ahead.
The C out on the adder, is it just not that's just not important?
That's actually not the C out. You're correct. That's the C out. That's the carry out, and that is not used at all. So I'm just leaving it there. So the carry output of the adder is not useful. All right. Any questions?
Is there a name for that circuit?
This circuit here?
Yeah.
I don't know whether there's a specific name for that. It's just a little register that has the ability to auto increment.
What happens when you exceed the 8-bit?
It rolls back to 0.
Okay.
Yep. Which is appropriate because my entire memory space only has 256 bytes, going from 0 to 255. So once you execute the last location, you're really out of locations to execute. And just like all processors, it will roll back to location 0 and start execution from 0 again. All right. Any other questions?
And we can have
is a location. All right. Any other questions? All right. If there are no questions, I'll do one thing that I keep forgetting to do, and I figure today is just as good as any day, right? I'm waiting for the time when I can use Google to take roll. So all I really have to do is to have a camera, and I just need to take a picture of everybody, and I just say, please, look at the camera, and then take a picture of the whole class, and then leave it up to either Facebook or Google to do facial recognition, and then go pick out all the names and automatically maintain my roll sheet. That would be the day that.
You just write it. You just write the program yourself.
I need to interface with the API of either Google or Facebook first.
Yeah.
Yep, and then you guys can help me tag names, tag faces, right? So now Google would actually have your attendance record.
They have everything else. That's
Might as well. Right? While you're in class, you might want to buy this. Take a look at this advertisement. Yes.
Can you run one more time the counter?
Okay. Let me cross out the wrong days. Sorry. Say again.
One more time the counter.
The counter. So do you want it to increment one more time? Okay. So let me just kind of cross out the columns that is not applicable. Oh yeah, I forgot to take roll on many days. There we go. Okay, so to increment the counter, you have to make sure that the enable pin is a 1 first, and then you clock the clock pin. So every time you go from 0 to 1, it updates. Okay. Yep, go ahead.
How's the top block is called in this circuit?
The what?
The top circuit with 0, A, and Z, and Q.
That's a register.
Register.
Yep.
Thank you.
So, how you get 2 zeros on a constant pin?
How do I get what?
2 zeros on a constant pin?
2 zeros in the constant here.
Yes.
That is that's a constant. It's a constant pin.
Yeah, I got that one, but I'm unable to add 2.
You change the address. You change the number of data bits, and then you change the value. Yep. Well, good thing everything is recorded. If you don't catch it the first time, you can always watch it again. All right. So, shall we move on? Subcircuit is okay so far? Okay. So let's go back to the other overall circuit in the processor. Now this looks a little bit more complicated because of the mux here, okay? The reason why there's a mux is because if I don't have a mux here, then the only thing I can do with this processor is to execute instruction in a very sequential way. Okay, it's only going to follow a straight line. Because if you want to do any type of branching, you have to be able to say, hey, you know what? I don't want to execute whatever instruction is next to this one. I want to continue execution over there. Okay, so in order to say over there, I need to have another input path into the PC and say, hey, we want to continue execution, but not with the next instruction. I want you to go over there to continue execution. So that's why there's a mux here, and also why we have a second input, to go to the PC if I want to. This line here is really here to choose what is the input that I'm going to use. So I'm not going to talk about who is controlling that input, at least not for the time being. Instead, what we'll do is we'll take a look at this line here and figure out, okay, so who is going to specify which location I should go next to get the next instruction. And we'll go ahead and click on this line here. And this is really a good feature of LogicSim, is you can click on a particular line and it will highlight the entire node. Now it highlights it here, but it's not really particularly useful because that's the input into a register. I call this the indirect register, which is not useful for the time being. We'll talk about that later. So we'll keep tracking this line here, and it goes all the way here. For those of you who kind of study the diagram or remember from last time when we talked about it, this is the register bank. Do you guys remember? This is the register bank, and it doesn't even stop only there. So this means that if I write my microcode correctly, there will be a way to specify an instruction and say, hey, take the output of one of the 4 registers that we have, okay, register A, B, C, or D, and say, and turn that into the next program counter. Okay, so you'll be able to do an indirect jump, which you cannot do in C or C++. There's no equivalent way of doing things like that in C and C++. The closest thing is a switch thing. Okay, but in assembly language, we can actually do that. But if you keep looking down this line here and figure out where it's ending, let's keep going. You will see that it is also coming into one of the input of the ALU, but that's just an input. So that means the bottom line is the other way to specify the PC or the program counter is using one of the registers. Are we doing okay so far with the pathways? Okay, because at this point I'm only interested in knowing, okay, what are my options? Instead of just going to the next instruction, what is the other option? How else can I specify the next location to execute in memory? And we can say that, oh, okay, the registers can do that. Okay, I can first load the content of a register from memory, and then I can copy that to the PC, to the program counter. That way I can now alter the path of execution. It doesn't have to be sequential anymore. All right, any other questions?
What's the difference between register bank and register?
What is the difference between?
Yeah, I mean the working function, because they have many input, output there. How does that work?
What? I'm sorry?
You said the register bank and just the register?
Yeah.
When he says the bank, it just means like a bunch of registers.
Yeah.
Yeah, so which means like several registers together working that way.
Well, the register bank is something that we looked at last time. This is the register bank, inside the register bank. And when you look at the main circuit, it kind of becomes this one little thing here, but it's actually the whole register bank. Okay. All right. Any other questions? No other questions? All right. Well, since we have a indirect register here, okay, which also hooks up to the MUX on this side, and then the other side of the MUX is also going to the address bus. If you kind of track down this line here, it also goes to the address bus. So now the question is, okay, what is the indirect register doing here? The indirect register, just like any other register, has a way to get updated. It has the enable pin here, and it has a clock pin here. The input is coming from here, which means, once again, we can use one of the 4 registers in order to specify the new content of the indirect register. And the output of the indirect register goes to the MUX, where it can potentially be driving the address bus. So the name of the indirect register is basically telling you what it's supposed to do. Okay, this is how we can implement indirect addressing. Now, we already know indirect addressing from C and C++, unless you took Java from before this class and never got any exposure to C and C++, then it will be a new concept to you. It's a pointer. Okay? So to access a location indirect means we are dereferencing a pointer. Now, let's take a look at this picture here and figure out what I mean by that. Okay? So let's take a look here, and what we'll do is we'll start with the register bank here. This is the register bank, which means I can specify the output of one of the 4 registers to this particular wire over here. That wire, in return, will go to the input of the indirect register. If I turn on the enable pin, which is this one here, and then I have a 0 to 1 transition on the clock pin, then the indirect register will be updated to the content of one of the 4 registers. Okay, big deal. Okay, so we can copy the content of one of the 4 registers to this particular special purpose register. So what is the big deal of doing this? Well, the big deal is the output of this register, which is this line here, goes into a MUX. And remember, a MUX is really just a switch. A mux is a switch where you have multiple input and only one output. So in this case, we have a control signal coming from here to basically specify, okay, do we want to use this input to present as the output, or do we want to use this input to present as the output? Now, if this is the input to present as the output, this output is the address bus, right? And the address bus goes to the memory chip. And as a result, we are now using one of the 4 registers to specify which address we want to access. In other words, we are using one of the 4 registers as a pointer. And this operation, what I just demonstrated earlier, is dereferencing a pointer. And that pointer is just whatever is in the register. Is that okay so far? Sort of?
Yeah, no, it's kind of, I might be confused. So the input, that top input that's connected to the indirect register on the mux.
Mm-hmm.
So.
Okay, let's go there. Okay, let's take a look at the picture. So,
Okay, yeah.
so you're looking at the input to the indirect register.
Yeah. So technically, that's the same line that's coming from the output of our register.
Of the register bank.
Correct.
Yes.
So when the register bank has an output, it's driving the input to the indirect register into our mux.
Not this mux here. It's going into the other mux. It's going to the mux.
The mux that's by the program.
By the PC, yes.
Yeah. So yeah. Oh, okay, no. So.
But those two paths are controlled by two different muxes. So in other words, I can update the indirect register, but not affect the PC whatsoever.
Yeah. Oh yeah, because that mux.
I can turn it off.
Yeah, turn it off.
Yeah. Or it can be redirected just to the 1+ PC from the app.
So I think where I'm trying to mesh it together is that maybe you're going to get to this, but so address comes from our register and it's like a pointer. So we can shoot directly to the indirect register, which can then shoot to that mux, which will go to our address. Or if we would like, or if it comes down to this mux, we would add it to our current program counter.
No, it will update the PC itself.
Oh, just.
Yeah, it would. Yeah, if let's say register B has the content of DF in hexadecimal,
Yeah.
if you pull the right strings and the right vowels and do the right coordination, you can put that content from register B into the PC into the program counter. So that will basically change the path of execution. So the next instruction you will execute is going to be at location DF in memory.
Oh, so you can bystep instead of going to
It's a
that
jump.
address.
Yeah,
Okay.
basically it's kind of like a jump instruction. On the other hand, if you make use of the indirect register, then you can do a dereference, because now you're taking the content of one of the registers, A, B, C, or D, in order to specify the address bus directly. So then you can now pull the content out of that location and say, okay, it's the address, I want the content at that location. Is that okay? Does everybody kind of understand what I just explained? Go ahead.
Now we have like access to only 2 registers. How about another 2 in a register bank?
Say again?
So like now we have only access to a data of 2 registers.
It's 2. Okay, are you referring to these 2 digits here?
Yes. No, like a two register INS register 1 and 1 is on the bottom. And in a register bank we have 4 registers. So how about the data of 2 other registers?
Well, the register bank has an input so that you can select one of the 4 registers to be outputting to this port here. This port is register output 0.
Okay.
And there's a select. I need to kind of look through the. There you go. So this is register select 0.
So we can.
So this is a 2-bit thing to go into the register bank, so that you can select which one of the 4 registers to present its content to register output 0.
Cool.
Okay.
Gotcha.
So we are talking about a lot. We're now talking a lot about the potential pathway between the components. We haven't really talked about the coordination of everything. Okay. So the coordination, we'll kind of leave it off to the last thing to talk about. but we want to identify all the things that we want to be able to do so far. Okay. All right. So let's see. I think we're almost done, with the overall processor design, except for the microcode engine that drives and connects everything. So we'll go ahead and zoom out, and just to make sure that we are not missing anything. And at this point, we are not missing anything in this picture. I explained what. Okay, let me just kind of count the components that I have just explained today. We explained this one. We explained the indirect register. We explained the program counter, the mugs, so that we can either continue execution with whatever is next to the current location, or we can jump to whatever location we want to based on the content of a register. And we have an automatic way to add to the program counter. The indirect register has only one way to get updated, and that is coming from the register bank. So that means we can utilize one of the 4 registers in the register bank in order to specify through the indirect register which location in memory we want to access. So those are the things that we have talked about so far in today's class. Okay, what about the content that is going out of the memory chip? So let's take a look. This is the data line or the data bus connected to the memory chip, the thick line, and you can see that it goes, it goes to a few places. Okay, so the first place that it does go to is going to the MUX. Okay, in fact, that's the only place that makes sense. So if you follow this thick line here, it goes to this MUX here, and if I select this input to be the output of this MUX, that MUX goes where? It goes to the input of the register bank. So that means the output of memory is going to go through the register bank in order to do anything. Okay? But there's one more path that it has to go to. Okay, if I just click on this line here, it goes to this one here. It's called the instruction register, INSREG, which is instruction register. The instruction register is tied into the microcode engine. Okay, it's an index into the microcode engine, and I'll talk about that next. Yep.
Have you designed it yourself, or is it already in the program?
Which
the
part?
Instruction register itself.
Oh, the instruction register by itself is nothing more than just a regular register. So if I zoom into the instruction register, okay, so let's go ahead and zoom into the instruction register. This one here, you can see that it is no different from any of the other registers. Okay, it is just a regular register. It is what I use it for and how I hook it up that makes it different. Okay? So the input into this instruction register, which is this part here, it goes to the data bus directly to memory. In other words, I can, if I need to, load the content of a memory location into the instruction register directly. I can do that. Okay? But what is even more interesting is what am I doing with the output of the instruction register? The output of the instruction register is broken up into a few chunks. Okay, so the few chunks, if you look at this chunk here, okay, let's click on the instruction register first. It has 8-bit wide. Okay, so each instruction is 8-bit wide, and of the 8 bits, I break it up into several components. This is the first component of an instruction. So what this means is bit 0 to bit 1 of an instruction is going into, well, you probably remember what about this diagram, this component here. It's going into the register bank. Okay, so if I scroll up a little bit, you will see better. So there we go. Okay, so this part of bit 0 to bit 1 goes into here, and that's register select 0. Bit 2 to bit 3 goes into this one here, which is register select 1. So that means a part of an instruction is dedicated, at least in this picture, is dedicated to specify which register do I want to output as register 0 or input, or which register do I want to output to register 1 of the register bank itself. Are we doing okay so far? Okay. What about the other 4 wires? The other 4 wires corresponding to bit 4 to bit 7 is going into, okay, so here's the fun part. Because I'm using a 0 here, another fun part, because I split up bit 4 to bit 7 from the instruction, and then I merge it with 4 zeros, which is bit 0 to bit 3.
So you create a byte from the.
So I recreate a byte, exactly. So an instruction is going to have 8 bits, right? Exactly. So this is an instruction. These 2 bits specify register 0 from the register bank. Okay, which one of the 4 registers do I want to treat as quote unquote register 0, either for input or output purposes? Because register 0 is the only one that can be useful for input purposes. These 2 bits are used to specify which register in the entire register bank can serve as the output of register output 1. Because I can have 2 outputs out of the register bank. These 4 is not really used for selecting registers. So instead what I do is I copy these 4 bytes, or 4 bits, excuse me. I copy these 4 bits down here, and then I add 4 zeros to the least significant bits. Is that okay? I copy these 4 bits, using the splicer and the merger, and basically add 4 zeros to the least significant bits. So I'm just playing a number game here, right? So the question is, what am I doing with this number here? Well, where is that going, right?
Go to bank.
If you track it down, it goes to
bank.
the 1
And the max.
tricky thing. It goes through a mux here, okay? And the output of the mux go to a MCC, which is microcode counter, okay? And the output of the microcode counter goes into the address bus of a ROM, okay? This is not RAM, this is ROM. In other words, it is a read-only memory, not a random access memory. You can only read the content, you cannot change the content, and not at runtime anymore.
So is that why you said it's called the microprocessor? So like that's for handling the programming of your processor.
It's how you can create new instructions. Okay. Now, the output of this ROM here is out of view for the time being. Okay, but when I expose that, then you go like, holy smokes! Look at all those wires going all over the place. Okay. Some of you can kind of quote unquote cheat because you have a computer in front of you and just go like, oh, okay, I can see that now. But if you look at the screen right now, if you look at the projector, okay, it's not clear what it is doing, okay? You might think, oh, it's just another data line going to the registers and whatnot. Not quite. Okay, every single bit of the output, except for one, I have one quote-unquote spare, it is all individual, okay? This one is also not individual. Bit 0 to bit 2 go to the ALU to select which operation, okay? All of the other ones have very specific purposes. So let's go ahead and pick up one of these, okay? So let's pick up, let's say this guy here. Track it down, and scroll, and it goes into here. This is an OR gate, and this OR gate, the output of the OR gate is going to specify the reset of the MCC, the microcode counter. So in other words, that is a way to reset the microcode counter to 0. Okay. Let's pick up another one. Let's pick up this line here. Okay. This is bit 7, and if you track it down, okay, it goes all the way around. I hope no one is getting motion sickness. And it goes into the enable pin of the indirect register. In other words, that one bit coming out of the ROM is what can enable in the indirect register and set it up to be updated. Are we kind of doing okay so far? Kind of having a general idea of what the output of the ROM chip is trying to do. So let's zoom out so that you can have a more global picture
What
of.
does your instruction code look like?
Okay, if you kind of zoom out, this is too much. This is probably be good. Okay, so if you zoom out enough, I can actually move this around too. So there we go. All right, this is good. So we can have a kind of like an overall picture, and you can see the output of the ROM chip, which is the output, the data port here, is all split up into individual bits. And those bits go all over the place. Because that is what glues all the components together and orchestrate all the operations. So it knows, okay, if we want to jump to a location of a particular register, we don't want to mess with the indirect register because this is not an indirect access to a memory location. I just want to change the program counter. And it will make sure that the enable to the indirect register is a 0. The enable of the program counter or the mux to the program counter is set up so the track is now programmed to the register output. And the enable to PC will be turned on, so the next clock, 0 to 1 transition of the clock line, will update the program counter.
The way that you broke out the output, is that?
It's somewhat arbitrary.
Yeah, so it's just a style selection, just a design choice.
Right. It's really kind of arbitrary. You know, I just broke out the lines, and in fact, I had to do this a few times. I had to change the width a few times just so that I have enough individual wires to do all the coordination.
But then, so since that's wrong and we're reading from that, that's hypothetically like related to the opcode of the processor.
That is correct. Okay, so the question now is what is the connection between an opcode and the microcode engine? What is the connection there, right? Okay, so the connection is right here. We know the instruction register has something to do with it because you can see that this wire goes all the way to this mux, and the output of this mux goes into the microcode counter, and the output of the microcode counter goes into the address bus of the ROM chip. So we know this particular register has something to do with it. And the purpose of this register is to serve as an index to the start page of the microcode corresponding to that instruction. It's basically like a chapter. Okay? So each instruction is really specifying one of 16 chapters in the microcode ROM. And then when you get to the chapter for a particular instruction, then you can specify individual pages in that chapter and say, hey, in order to execute this instruction, we have all these steps to perform. Okay, if an instruction has sub-steps or micro-steps, how do we control the execution of the micro-steps? Well, same mechanism that we have seen already, because some of you may recognize this construct from before. If you look at the microcode counter and look at this adder here and look at this mux here, does it look familiar to you? It should. Okay. So
counter.
Exactly. So once again, we have the mechanism. We have two important mechanisms here. The first mechanism is a self-incrementing mechanism. Same thing as last time. Okay. If you have the enable pin of the microcode counter turned on, and you clock the clock pin, it will increment and have the mux set up to the output of the adder. Then it will increment the counter of the microcode counter. Okay. On the other hand, if you have this wire turned to a 1, then it will pay attention. Excuse me. If you turn it to a 0, then it will take it back. If you turn it into a 1, it will pay attention to this bus here, and that bus is this constant here. It is made out of 4 zeros as the least significant bit, and using whatever we have in the instruction, the most significant 4 bit of the instruction, as the most significant 4 bits of that number. And that's why it is a chapter. Okay, and in each chapter you can have 16 sub-steps in order to implement an instruction. So this is indeed a very simple processor because you can only have up to 16 instructions, and each instruction can have 16 sub-steps. But the sub-steps have to do with, in order to do this, we have to turn off all of these things, turn this on, clock it. Okay, in the next step, we'll do something, we turn this off, turn that on, clock, and so on. So the microcode engine is the one piece that glues all the other pieces together and do the coordination so that the processor can now actually do sensible things. Are we kind of doing okay so far with the overall idea of what a microcode engine is. Yep.
So one more time, that mux determines whether the MCC pays attention to the incrementer or what is the other part?
Basically, it is the instruction register.
Okay.
Because a part of the instruction register directly controls which register of the register bank I want to use. The other part goes into here so that I can select which operation I want to use. Are we still doing okay so far? Okay. So focus on the overall picture first, okay? Because the detail, you can download the file and really go through the details. Okay, so that part is not really as important, but it's the overall picture and the reason why we have the microcode engine that is more important. Okay, because now if I zoom out, once again, I'm going to use the analogy of an orchestra. Okay, so overall speaking, we have a lot of instruments here, right? We have, a double bass, a cello, and then we have, flutes, clarinet, and so on and so forth. So we have all of these little components here, but you don't want all of these musical instruments to all play at the same time, and it's not going to be, they would end up fighting each other, right? Okay, remember bus fight? Okay, so so now we have a bus fight with musical instruments. My bet is on the trombone. Well, it has the longest reach.
Yeah.
Yeah, that's important. But if you want to, if you want to be defensive, you want the double bass. You can hide behind it. Tuba. Oh yeah. Okay, so the conductor is this guy here. The conductor is the microcode engine. This is the conductor. The conductor consists of these wires and also where they connect to. Okay, so if you trace each wire, what they connect to, those are the control mechanisms. What does it make this little microcode engine here? That's what the conductor is reading. That's what the conductor is reading from in order to tell the individual instruments and say, it's your turn to do something here, it's your turn to do something over here, and so on. So are we kind of doing okay so far with this? Okay. So the difficult or the chore of getting this processor to work, and I can only get two of those things done, is the implementation of the instructions. Okay? Because now you have to think about the sequence of doing something. Okay? Okay, I want an add instruction. Okay? Simple enough, right? So an add instruction, okay, you can either write it down, it's all getting recorded anyway. If you want to do an add instruction, and I want to keep it as simple as possible, I want to pick two registers out of the register bank to feed into the ALU. Perform the add instruction, take the output out of the ALU, and store it back into one of the two registers that served as the input into the ALU. That's all I want to do. Okay. Let's see how what is the sequence to do that. Okay. So we'll take a quick look at that sequence. First thing first. The first thing you need to do is to decode the instruction. Okay. So we'll go to the instruction register here. I'm going to zoom in again just so that we can see the individual components. So the first thing you have to do is to pay attention to the instruction register, because bit 0 to 1 will specify one of the two registers, bit 2 to 3 will specify the other instruction, and the next thing we have to do is to turn on those outputs, okay? Because you can select the registers all day long, but if you don't turn on the output enable of those registers, nothing is presented to the input of the ALU. So that means these wires, I have to kind of remember which one those are. So this wire, and I think it's the next one, but yeah. So these two wires also have to be turned on in order for the two selected registers to present the output to the ALU. Okay, so that's one step already. Yep.
So to turn it on, you just simply click on it?
You have to turn those into a 1.
Yeah, but in order to turn it on into a 1, you just click on them?
No, you have to specify the microcode to do it now.
Okay.
So that's why that's why it's a real chore to specify the microcode, Because now you have to specify, okay, I need to turn these things into 1, wait for the clock to clock, and then I turn these off, turn those on, clock, and so on. Okay. So what is the next step? Now I'm presenting the output into the input of the ALU. So now the focus is on the ALU itself. This is the ALU. And the two inputs of the ALU is this one and this one here. Okay. And the selection of the operation is coming from this wire here. And this wire is directly going into bit 0 to 2 of the microcode. Okay. So now you specify, you want to add instruction, you want the subtraction instruction, and so on by, programming those 3, 0, 1, 2, those 3 wires into the microcode of instructions. So 3 bits of each microcode step can be used to specify which operation do you want to, focus on. Okay, so that would be the next step. It can be done simultaneously with the other step too. Once the ALU is done, okay, so you do have to allow some time for the ALU to do its job. When the ALU is done, the output is now presented to the output of the ALU. So it's time to control this mux so that it is no longer reading from the data output of the memory chip. Instead, it is selecting the output of the ALU, which will now complete a path back to the register bank. And then you, let me pick out which one it is. Then you have to enable register write enable, so that whichever register you're supposed to overwrite now has the write enable pin turned on. And then the next one is the clock, right? You have to go from a 0 to a 1 as a transition to update the register that is supposed to store the result. That is a sequence to perform a add instruction or subtract.
If they write down the answer, just keep the old value.
Sorry?
If that
The other one keeps its old value, yes. Yes, you only update one of the 2 registers. And I think it's register select 0 that can serve both as the output and the input. All right, what about just reading a byte from memory into one of the registers? Well, now you have 2 choices, okay? Now you can specify, do you want to do an indirect access, or do you want to spell out which location as a part of the instruction to access? Okay? If you want to spell out the instruction, then what you need to do. Okay. Let's talk about the one single instruction that you need in order to read from a single location. So the instruction specifies which location is not stored in the register. Okay? So we're going to read from a fixed location. Okay, this is what we want to do. Now, if you want to read from a certain location in memory, then you have to control all the lines going to the memory bus. And the memory bus is all the way here. So now you have to control the address bus. Now, but remember, you are going to use one cycle, or you're going to use one read operation just to read the instruction itself. Okay? So that means the next thing your microcode has to do is to say, increment the program counter. Because now your instruction actually is made out of 2 bytes. Because the first byte is the actual instruction. The second byte is the address of the byte that you want to read from. Because this is not an indirect, this is actually spelling out as a part of the instruction where you want to read from. So you need to increment the program counter, so now you need to control the circuitry, the mugs, to specify, hey, go ahead and increment the program counter because the instruction is already read, it's okay, but now we need to read the next location. Then you need to read its location, and I don't have a path directly into the indirect register, so that means we cannot really implement this, we have to store it into a register first, and then we can use the register indirect, put it into the indirect register, and then access the content at that location.
But so in a full implementation, that address would get driven back to the indirect register instead of going back to
Right.
Instead of coming out of the data bank and going back into registers.
Correct. But we don't have a pathway to do that, I don't think. So if you highlight the data bus, it goes into the MUX. So let's say the MUX is switching to this one here. The other side only goes into the input of the register bank. So that means there's no direct way to update the indirect register. Not with this architecture. Okay, you can modify it so that it does.
Could you just draw one? That probably.
Now you can just draw the line. The question is, once you draw that line, how do you you can draw that line, but the indirect register already has a path coming from the register bank.
So you have to at least throw a MUX in there.
So you will need to use either another MUX or, let's see.
Can we just change the indirect value?
Registers can't have two inputs?
They cannot both be driving. That's the limitation.
Oh, then
okay.
you have to do that.
So we might be able to get away with it because the output of the register bank has its own output enable. The other one, yeah. So we can turn off the output enable of the register bank, and then leave it up to just the data bus to drive it directly. Then we can still do it. In other words, I can now, make an in-place change to this circuit here. If you're doing this for a job, I would not do this, but at least not backing it up first. Okay, so what I can do now is I can go directly from here to here.
Because that is coming from the output. Oh, that's coming from data, right? That output of that MUX.
That MUX is data, is from the data bus. That bus is from the data bus. So that means, I can use this wire to select one of the two, and then the indirect register, because what I need to do is to make sure that we don't end up with a bus fight. And the only two components that can drive this particular wire, if you just kind of highlight the wire, this one here. If you highlight the wire here, this is all the things that can drive it. And this one is the input, so it's not going to be a problem. This is an output, which can be a problem. This is an input, it's not going to be a problem. This is an output that can be a problem. So we have to kind of make sure that the MUX, the way it's set up right now, is going to cause a problem because this is always going to output. So we cannot do that. Yeah. So you always have to go through a register in order to do the indirect.
So this one, for this one, it would, if that had to be implemented, it would be better to just throw a MUX into the indirect.
Correct. Now, but when you add a MUX, you are adding one more control signal. So that will use up the only spare wire that I have from the microcode engine. And that's why it was so tedious to design the microcode engine, because I end up running out of wires. It's like, oh, okay, we need to make it wider. Okay. All right, so that cannot be done. We cannot have a single instruction that can just go to a certain location and read from that location. What about reading from a location and putting into a register? Can we do that? Yeah, we can do that. Okay, so we have, so this is a true RISC architecture, because for certain things that even most RISC architecture can do in one single instruction, we have to break it up into even more, sub-instructions. All right. Are there any questions? Has anyone opened up the spreadsheet and take a look, of what is inside the spreadsheet that goes along with the zip file? It's inside the same folder? No?
No.
Okay. Are you guys ready for that? Advil, Tylenol, anyone? Yep.
I have.
You ready? Okay.
I've taken a spreadsheet and
okay.
dug into the XML.
I was kind of, when you said I have, I was thinking that you have, medication that you have ready here. I think I have naproxen sodium, 550 mg. So I think this will help. Take one tablet 1 hour before appointment, and guess what appointment that was? Gum transplant. If it can handle that, it can handle this. For those of you who have not had the experience of gum transplant, it's actually not that bad. I did not take the medication before the gum transplant, and it turned out okay. It was only on the third day that it was really painful. Every time I tried to rinse, it was so painful that tears just rolled out of my eyes uncontrollably. Okay, so I called the office because I also saw some yellow stuff, kind of oozing out of the area. So I thought, oh no, I have infection of some kind, right? So I called up the office and I described exactly what was going on. It's like only when I'm swishing it with the special rinse, that I can sense a lot of pain, and some kind of yellowish stuff is coming out of it. But otherwise, it's just kind of red and not really, have any sign of infection. And I think the nurse on the other end, just kind of chuckled. And then she said, I think you're fine. Okay. And then she asked, so how did you rinse for the past 2 days? Because it was on the third day that I had this problem. And I said, well, of course I rinse, rigorously because I don't want to have any type of infection. And then she said, no, don't do that. Don't do anything, with force. Okay. Don't do anything with rigor. Yeah. Just treat it gently. Okay. Let gravity do the work. And I was squishing, like big time. It's like that. So she was saying, I was tearing up, nature's Band-Aid every single time that I swoosh, because I was doing it with such force. The tissue is trying to heal itself, by all oozing out all the yellow stuff. That's actually the healing cells. It's trying to actually repair the incision point, and I've been swooshing it away every single time. So once I stopped doing it, it's fine. It was like, okay, cool. The rest of the week was easy. So I only have myself to blame, about being painful, because otherwise the first day is supposed to be the most painful day, and it was okay, but it wasn't really much. All right, so getting back to this, the spreadsheet. Yes. See, I remember what I was supposed to talk about. All right, the spreadsheet. There we go. Okay, the spreadsheet is ODS, which means you have to either use LibreOffice, OpenOffice, or a late version of Microsoft Office should also be able to open it.
Emacs, it looked like letters. It was just like 0. It wasn't like
1.
Okay, there's a whole bunch of zeros and ones and a lot of indexing, and I'm building this tool as a tool for myself so that I can write new instructions. Okay, so when you look at each column, okay, it specifies, okay, the top row specifies which bit we are talking about. Bit 0 to 2 is ALU operation selection. Bit 3 hooks up to MCC clear, which means I'm resetting the microcode counter back to 0. Back to the top, because that actually has a special meaning. That's the code to fetch the next instruction. So every time I'm ready to execute the next instruction, I have to reset it.
Oh, that's the opcode for the process of fetching the next instruction, which is going to.
It starts the whole sequence of fetching the next instruction, but without decoding it.
Okay.
Yeah. The decoding part has to do with this. This is the decoding.
When you broke down.
But before you can do this, you have to get it into the instruction register first. So when I reset the microcode counter, that few steps over there, which is basically chapter 0 of the book, basically just talks about how do we load the next instruction into the instruction register, then we can start to decode.
To stay with the analogy, the preface or introduction?
It's really the first part. It's the prefix, I guess. There's nothing before that. Okay. Bit 4 is register 1 output enable. Bit 5 is register 0 output enable. Bit 6 is register write enable. Register 7, bit 7 is indirect register write enable, and it goes on and on and on. Okay. So once I figure out what instruction I want to implement, I first have to write down the instruction, like using a text editor. Okay, just in plain text, I write down what I need to do, and then I have to specify all the zeros and ones. And you can see that there are many zeros and ones that I have to specify here because I think there are a total of 17 bits, individual bits, going into all the different muxes, enable outputs, clocks and whatnot. So there are 16 bits altogether, and this is a equation. If I double click on it, you will see it. So this is an equation. Yeah, it's kind of long. Okay, but this converts the zeros and ones, which is a binary number, back into a single value, a single quantity, and it is displayed in decimal in this case. It's just a decimal number. And then the next line, which is this one here, that's the hexadecimal version of the same quantity. So I separated it into two steps here just so that I can double check things a little bit easier.
I don't know if I'm mixing stuff up, but so your instruction set is 16 bits long, but isn't that
it's 17-bit wide. The output of the ROM chip is 17-bit wide.
The input coming into MCC is only 8 bits.
Right, but that's the address. See, the width of the address bus only has to be wide enough so that you can address enough locations. But it does not tell you how wide is each location. The data bus, on the other hand, dictates the width of each location.
Okay, so we have 256 locations, but each one holds 17 bits.
Yes, the way you set it right now. So that's how I wrote the microcode for the few instructions that I have here. We can take a quick look at what instructions are currently implemented. So we have a fetch, which has to be done. Okay. So the fetch sequence is not really an instruction by itself. It is something that you have to do in order to load an instruction into the instruction register and start the decoding process. Now, once it is decoded, then you can get to the individual chapter of the actual instructions. Okay? So the actual instructions, there are only two instructions. One is load register with an immediate constant. In other words, you are basically saying, I want register B to be 5 right now. Okay? Not the content of location 5, just 5. Okay, so this will basically make register B 5 if you specify the number and all the other stuff correctly. The next instruction is this one. It is store indirect. Store register indirect. It will store a particular register, the content of one register, indirect using another register, potentially another register as the address. So you have to specify two registers. One register to specify the content, and then the other register to specify which location in memory is it supposed to update. Okay, let me put it up this way. Okay. Okay, it's basically doing this in C or C++. This is one register. This is another register. So it would use one for dereferencing and then use the other register for the content to go to that location. This is why C and C++ is one of the most important prerequisites of this class, and because you don't get exposure like this in Java. Yep. Are we still doing okay so far? Okay. So if you go back to, yep, go ahead.
So do Java have another variant of pointers, or they?
Java has no pointers. It has what we call, what are those things called? References. And it's not the same thing because you cannot have an explicit dereference like this. So in Java, it's all handled kind of implicitly. The point is they don't want you to play with memory like any way you want to, but at the same time, they take away the low-level operation that you need to understand in order to get to this part of this class. Okay. All right. So getting back to the machine, which is a computer. Yep. Getting back to this one here. So I do have most of the microcode already loaded here, and this is how you write instructions back in the good old days. Okay? In other words, you look up a spreadsheet, not this one, let me turn on, get rid of all the stuff that I don't need. Now, go in. Yep, that's that one. That one. There we go. Okay, so what you need to do is you have to, basically remember 0, 0, 0, 0, 1. If you specify with an instruction, if you specify this code here as the most significant bits, it is a load register with a constant instruction. If you specify 0, 0, 1, 0 here, it is a store register indirect into memory instruction. And you have to remember it, okay? Now, this is not hard, right? Because you can only have up to 15 instructions because the first instruction cannot be used. It is the prefetch stuff, right? So we only have 15 instructions here. What if you're dealing with the Intel processor? What if you're dealing with the Pentium line processor with all the extensions? Then you have hundreds of instructions to remember. And each one, I'm sorry, each one is not a 4-bit number. They have instructions that that will take up just the instruction itself. The bit pattern will take up 32 bits. Okay? And every time you want to write an instruction, you have to look it up and find out, okay, what are the zeros and ones corresponding to this instruction? Sound fun? That can be a little bit painful on the painful side, because if you make a mistake, no one's going to tell you, hey, this is supposed to be a 1 here, not a 0. So you just specify something that the processor will interpret as something other than what you intend, and your program is not going to work.
You have to go back and do everything.
And then you don't have any debugger either, right?
There's another bug around this?
So, yep, go ahead.
Or it works, but not as intended.
Well, not as intended, exactly. The whole point is it's not as intended, okay? But this is also a good place to explain why we have such a thing called an assembler, okay? What is an assembler? I mean, by the way, the title of this class is Assembly Language Programming, right? That is not assembly language programming. That is machine code programming or opcode programming, because you are at the same level as the processor. You're now understanding things in bits, in zeros and ones, highs and lows, okay? But it's not very friendly, okay? Because okay, let me magnify the text a little bit here. Okay, there we go. So I use LD to represent load, okay? Because we are reading from some place and we're putting that value into a register, okay? That is called a mnemonic. Okay? It's basically a very obscure short form of a name of a word, but it is still much better than 0001 as a binary number. The next one is ST, which stands for store, okay? And once again, if you only have 16 of these things to remember, you will quickly remember LD is load, ST is store, because there's not a whole lot of room for ambiguation or confusion, okay? Those are called mnemonics. And assembly language programming is all about using mnemonics and actual numbers in base 10, in order to write your code, instead of having to look at all the bit patterns and say, okay, which register am I talking about? Well, there's no such thing as register ABCD. There's register 00, register 01, 10, and 11. Okay? But using an assembler, now you can associate symbolic names with the registers. So it's register ABCD, and you can use syntax to help you so that you can kind of help reduce the amount of ambiguation or room for error. That's assembly language programming. Okay? So in other words, having an assembler is already a huge step forward in terms of programming a computer, because without an assembler, you would have to basically specify zeros and ones, which makes it much harder to write programs, let alone debugging a program. Are we doing okay so far with all this stuff here? Now, before this semester, well, I should say before last semester, I never really talked about all the low-level stuff like what you're dealing with here. So we just jumped into assembly language programming right away, and guess what? We have problems, okay? Because there's no distinction. People cannot distinguish what is a indirect operand as opposed to what is a direct operand. When you specify, go to that location. No. go to that location or use a register to indicate where you're supposed to go. But looking at instructions like this, now it is really clear we can specify instructions and make it very clear exactly what the instruction is going to do. So we are looking at things from a bottom-up view instead of a top-down view with all this stuff. Are there any questions about the microcode engine and how it ties in everything within the processor?
How would we get LogicSim to run that?
LogicSim does not run this. This is mostly for our purposes. So when you want to specify a program in LogicSim, the way you do it is you click on the memory chip here, and you say load image. And I have one program here that has the load register from memory instruction. So you open it, and now it specifies the content. And now you can actually run it. Now to run this, how do we run a program like this? Okay, this is something that you might want to do before Thursday, just so that you're familiar with the tool itself. Okay, so when you look at this entire picture, there's really not a whole lot of stuff that you can do other than loading content into either the RAM chip, or if you want to upgrade the ROM chip, you can also have your own microcode implemented. Okay, but the only two pins that you can actually play with, let's take a look here. There are two pins. One is a reset pin, which means we are resetting the whole processor, the memory. We're starting from the beginning. And the other one is a single clock pin. And you read it right, a single clock pin. We don't have one clock pin to the indirect register. We don't have another clock pin to the instruction register. We don't have another clock pin to the memory module. It's one single clock pin. It's by coordinating the enable pin and the chip select pin that we can use a single clock pin to do everything. Okay, but that's how a processor is designed. There's only one main clock inside the processor. So the way you run this program is just clock this thing, right? Click, 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 and now you can see how it it's actually exercising the different pins and actually doing something with the registers. Unfortunately, we cannot really tell the inside of the processor. So when you run this program, you can only infer the content of registers by looking at the memory content if it is right into memory. Okay. So you might want to do this a few times. I will go to the lab. In case anyone has any questions, I will kind of go through the steps of doing this, because your homework assignment is going to involve writing new microcode, new instructions. Okay, I'm not going to just say on Thursday, okay, implement this whole laundry list of instructions, because I have taken location 0 cannot be used. I have written 2 instructions, so that leaves 13 possible instructions for you guys to implement. So I'm not going to be so cruel to give you like 13 instructions, say, okay, these are the 13 instructions I want you to write. And on top of that, write a program and load it into RAM to do the following, like decrypting DVD or something like that. So what I'll do is I will kind of break in gently. We don't have an add instruction yet. Okay, so maybe that will be the first instruction. Okay, so you might want to get familiarized with the tool itself, the overall schematic of things, and just say, if I were to implement an add instruction, adding 2 registers and store the result into the first register, which is register 0, how would I go about doing it? Okay, that would be a good thing for you guys to do before Thursday. And if there are no questions, I'm going to stop the recorder at this point, and I'll go to the lab. And once we get to the lab, if you have questions about LogicSim itself or the schematic of this processor, I can answer those questions at that time.
I think you didn't have to